Okay, so here's a trick with polyatomic ions. You have to look here where it says, remember to add to the total number of valence electrons in negative ions, because the way you make something negative is by giving it extra electrons. So let's take a look at number 1. Alright, the first thing I'm going to do is add up all the valence electrons. Sulfur has 6, plus oxygen has 6, and I have 3 oxygens. So that right there would be 24, but don't forget, I have a -2, so I'm going to add 2 more electrons for a grand total of 26 valence electrons to work with. So just like I did before, I'm going to put sulfur in the middle. I'm going to put the oxygen symmetrically around it. There's 1, there's 2, there's 3. I'm going to connect them to the center with single bonds. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. No problem. Now one thing I'm going to do with these is I'm supposed to bracket it off like this and put -2 to indicate that this entire molecular structure has a -2 charge to it. So it's basically like a ginormous ion that carries a -2. Now the name of this, you just have to learn them. SO3, if you look on your periodic table, is called the Sulfite ion. So unlike before, these are not going to end in ides. Let's look at our next one. I'm going to add up all of our electrons. We have 6 for sulfur, plus 6 for oxygen, and we have 4 oxygens in this case. 2, 3, plus another oxygen. So we have here, let's see, 30, and we have, is that right? Yeah, we have 30, and we have another 2, so I have a total of 32 valence electrons that we have to work with. So let's draw SO4. I put S in the middle. I'm going to put the O's symmetrically around it. I'm going to connect the periphery atoms to the center with single bonds. So what I've used up so far is 2, 4, 6, 8. Now I'm going to distribute my remaining electrons in pairs. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And then I bracket the whole thing off. And I say, you know what, it's got a -2 charge. This one, if I look up, is called Sulfate. So general rule is ones that have the most number of oxygens they can have are called end in 8s, and the ones that end in 8s, and the ones that have less end in ites. So if we look here, I have 2, one with 2 oxygens, one with 3. So this one will be nitrate, and this one will be nitrite. Let's try the nitrite first. So when I count up my valence electrons, I have 5 for the nitrogen, plus 6 for the oxygen, and I have another oxygen, and it has a -1 charge. So that means I'm going to add 1 more electron. And I'm sorry that negative charge means to add, but remember, the way you get a negative charge is by adding extra electrons. So what we have here is a total of 18 electrons that we have to account for. So we're going to put the nitrogen in the middle. We are going to put the oxygen symmetrically around it. We're going to connect the outside to the inside with single bonds. We're going to distribute the remaining electrons in pairs. So far I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18. Aw shucks, I just ran out of electrons, and look at this. I have a missing pair. So when there's a missing pair, what do? You add a bond and you erase a pair. And now I have, everybody's got an octet, if you look, everyone does. And I am going to bracket it off. I'm going to put a -1, and we're going to call this one the Nitrite Ion. Let's keep going here. I have, oops, that's not right. I have 5 valence electrons from the nitrogen, plus 6 from each oxygen, and there are 3 oxygens, and it has a -1 charge, so I'm going to add 1 more electron, so that gives me 24 electrons that I'm going to work with. So I'm going to put the nitrogen in the middle and put the oxygen symmetrically around it. Connect the outside and the insides with single bonds. I have used up 2, 4, 6. Then I'm going to go 8, 10, 12, 14, 16, 18, 20, 22, 24. I just ran out of valence electrons, and look at this. I need more electrons. So, since I'm 1 pair short, what I'm going to do is I'm going to add a bond. Doesn't matter which oxygen you add it to. And I'm going to erase a pair. And then I'm going to bracket the whole thing off. And I'm going to put -1 on it. And this one is called nitrate. Oh, our next one is different. It has a positive charge. Not many polyatomic ions do, but this is one that does. So I'm going to add up my valence electrons. I have 5 for nitrogen, plus 1 for each oxygen, and there are 4 oxygens. Now ask yourself this. How do you give an ion a +1 charge? Why, what you do is you take away an electron. So I'm going to subtract 1 from this. So what I get here is 5 plus 1 is 6, plus 1 is 7, plus 1 is 8, plus 1 is 9, -1. I have 8 valence electrons to operate with. As always, I'm going to take the element that's over here and put it in the middle. I'm going to distribute the hydrogen symmetrically around the center. All 4 of them. I'm going to connect the outside to the inside with single bonds. Let me see how many electrons I have left. 2, 4, 6, 8. Hey, wait a second. I don't have any electrons left, but when you look at it, everybody's happy. Remember, this is what happy hydrogens look like. They just want a single bond going to them. That's 2 electrons. That's all they want. So that's all I had to do. I bracket that off, label it with a +1, and this one is called ammonium. I hope I spell it right. I hope there's 2 M's. Ammonium, as opposed to ammonia. Ammonia is a compound, not a polyatomic ion. Well, let's look at this next one here. This next one, I have, let's see, carbon has 4 valence electrons. Nitrogen has 5. It has a -1 charge, and the way you get that is by adding an extra electron onto the structure. So that gives me a grand total then of 10 valence electrons to work with. So I'm just going to put these 2 side by side. Here's C, here's N. You know what? I don't like that. I'm going to erase this here. Alright, I'm going to get a little more distance between them. Here's C, here's N. I'm going to connect them with a single bond. That's 2. 4, 6, 8, 10. And if you notice, I am 2 pairs short of having my nitrogen be happy. So for each pair I am short, I am going to add a bond. So I'm going to add 2 bonds. And therefore I'm going to erase 2 pairs of electrons. And there you have it. And you know what? I'm going to erase these here and put them over here because I think it looks better. You don't really have to. And then I'm going to bracket this off and give it a -1 charge. And this one has a name you might have heard of, cyanide. Okay, now we have, here we have phosphate here. So we got phosphorus, which has 5, plus oxygen has 6. That's a 6. And we have 4 of those. Plus, we have a -3 ion, which means we have to add 3 more electrons. So what that gives us then, I hope I get my math right here, we have 6 and 6, that's 12, 24, plus 5, that's 29, plus 3 is 32. So we're going to put the P in the middle, surround it with oxygens. Connect the oxygens to the phosphorus with single bonds. Now, we have used 2, 4, 6, 8 of our 32. So we're going to do 8, then 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We're done. Look at that. Single bonds. Easy cheesy. Here we go. And we're going to say this is -3. That's a terrible looking 3. And this is called phosphate, which you've probably heard of because it's used in detergents. Phosphate. And now we have the carbonate ion. So we have 4 electrons from carbon, and then we have 3 oxygens, each with 6 valence electrons. And since it's a -2, we're going to add 2 more. So that gives us a grand total of 24 valence electrons to work with. We're going to put the carbon in the middle. We're going to put oxygens around it. We're going to connect them to the middle with single bonds. So we've used up 6 of our electrons, so we go 8, 10, 12, 14, 16, 18, 20, 22, 24. Will you look at that? We're missing a pair of electrons right here. Carbon's not happy. So since we're 1 pair short, we're going to add 1 bond, and we are going to erase 1 pair of electrons. Now everybody's happy, and we can put a bracket on it. Put a -2 here. And this ion happens to be called the carbonate. A rather important ion. Okay, now welcome to the back side of this. Now here's a place where we see when you have more electrons, it's the 8 ending, and when you have fewer of them, it's the ite. So this is chlorate and chlorite. Now these ones are a little bit unusual because chlorine is going to take a central role here. So let's go ahead and draw this then. First of all, we have 7 valence electrons from the chlorine, plus 6 for the oxygen, plus another 6 for the other oxygen, plus 1. And that gives us a grand total of 18 valence electrons to work with. So in this case, we're going to do something we don't usually do. We're going to put the chlorine, which is a halogen, in the middle. And we're going to put the oxygens on either side, connect them together with single bonds, and that's 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah, there we are again. Look, chlorine is missing a pair. So I'm 1 pair short, so I'm going to add 1 bond, and I'm going to erase 1 pair. There we go. And I'm going to go ahead and put a bracket around this bad boy. And I'm going to put a -1. And this one is called the Chlorite Ion, as opposed to the next one, which is the Chlorate Ion. So for the Chlorate Ion, what I find is I have 7 for chlorine. In this case, I have 3 oxygens. And I'm going to add 1 more electron because it has a -1 charge. I'm going to put the chlorine in the middle again. I'm going to put an oxygen here, and an oxygen here. Connect them with single bonds. And then I'm going to distribute my electrons. So I've used up 2, 4, 6, 8, 10, 12, 14, 16. Wait a second. I didn't count up my total. Okay, what's my total here? I've got, let's see, 18, 19. I've got 26. Oh, Eric. You should have been careful there. So now I got to go back and recount. I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Hey, it all worked out. And this one here has a -1, and this one is called the Chlorate Ion. Now, in all fairness, I do need to point out that chlorine doesn't really follow the octet rule in this particular example. This is how I would expect you to follow the rules that we've been learning, but it turns out that chlorate is an example of an exception to the octet rule. But don't tell anyone, we're just going to go with it the way it is. Okay, now using polyatomic ions is really no different than any other ion. It's just I have to look at a different part of my periodic table to see what the charge is. So ammonium has a +1 charge, whereas sulfur has a -2 charge. So I put the positive ion first, NH4 has a +1, and I have sulfur, which is a -2, and we swap numbers. I don't like this 4, hang on a second. Alright, and so I'm going to swap numbers. That means I need to have 2 ammonium. So the way this 2 here is going to come down, remember we're going to swap and simplify. I need 2 ammonium, so I'm going to put parentheses around it and put the 2 here. And what that means is I have 2 ammonium ions, each with a +1 charge, and I have 1 sulfur with a -2 charge. Now the name of this is simply ammonium sulfide. I just say the name of the 2 ions. So let's try the next one. Nickel is a +2 ion. Phosphate is a -3. So I put the positive ion first. It's a +2. Man, I'm doing a terrible job here. And I put the phosphate second. It's a -3. And we simply swap numbers. So I'm going to need 3 nickels, and I'm going to need to have 2 phosphates. Remember, you swap and simplify. 2 -3's cancels out 3 +2's. Now you just say the name of the 2 ions. Now this happens to be the nickel 2 ion, and then phosphate. Next one, we have chlorite. That's a -1. You know, I'm going to swap to a bigger pen. Hang on a second here. I might regret this, but let's see what we got here. Okay. And barium is a +2. Well, I already regret that. +2. Yeah, we're going to switch back to the other pen. Alright, let's go back to the other pen. Sorry about that, gang. Okay. So, I'm going to put the positive one first. That's Ba, which is a +2. And I'm going to put the chlorite second, ClO2. That's a -1. We're going to swap numbers, so I need 1 of these, so I can leave it the way it is, and I need 2 of these. So I'm going to put this in parentheses and write a 2. That's how I indicate that. And so now what I've got here, if you look, I have 2 -1s, which cancels out 1 +2. And barium is only +2. It can't be anything else, so I just say barium. And then I say chlorite. Alright, our next one here, we've got aluminum is +3. Cyanide is -1. I put the positive one first. I put and it's a +3. I put the cyanide second. It's a -1. We're going to swap numbers. So I need 1 aluminum and I need 3 cyanide. So I put a parentheses here. And I put a 3. 3 negative 1s cancels out 1 positive 3. Aluminum can only be 1 charge, so I just say aluminum cyanide. There you go. Now, sulfate here is a -2 ion, and copper is usually a +2, although it could be +1. I put the positive ion first. I put the negative one second. And since they're both 2s, they would cancel out. So I mean, I could swap and put a 2 here and a 2 here, but I just have to reduce it to a 1-to-1 ratio. So I'm going to call this one here copper Roman numeral 2, so I don't confuse it with copper 1, copper 2 sulfate. Next one we have iron. Iron is usually a +3, although it can be a +6 or a +2. We have chlorate, which is a -1. I put the positive ion first. It's a +3. I put the chlorite second. It's a -1. So I swap. I need 1 iron and I need 3 chlorites. So I put parentheses 3. And I'm going to call it iron 3 chlorite. Chlorate. I apologize if I've been calling it chlorite. That'd be my bad. Alright, I'm going to move this whole show up a little bit here if you don't mind. In fact, I'm going to expand a little bit because I need some room here. Okay. So our next one, titanium. Titanium, I believe, can be 2 or 4, but it's usually a 4. You know what? I'm going to check that. Okay, I was right about the usually a +4, but sometimes it's a +3. All right. Well, now what I have here next is sulfite. Sulfite is a -2. So I put the titanium first, which is a +4. I put the sulfite second, which is a -2. Now watch what happens here. We're going to swap, and then we're going to have to simplify, because when I swap, I get a 2-to-4 ratio, but a 2-to-4 ratio can be simplified to a 1-to-2 ratio. So I need to get rid of this here and change it over to a 2. So remember, we swap and simplify. And then I'm going to call this one here titanium 4 sulfite. I guess I should have put that in parentheses, huh? Alright, we have hydroxide as -1. We have calcium is always +2. I put the calcium first. I put the hydroxide second. This is +2. This is -1. We're going to swap. So this is going to be a 1 and this is going to be a 2. So I got to wrap this in parentheses. Put a 2 here and call it calcium hydroxide. Notice, because this is ionic compounds, I don't have to tell you how many of each there are. Ooh, look at this. This often freaks students out. What? I got 2 polyatomic ions. Can you do that? The answer is yep, you sure can. That's a +1. That's a -2. No problems. Put the positive one first. Just be chill. No biggie. That's a +1. And carbonate is a -2. And we do what we always do. We're going to put 2 of these and 1 of these. So I need to wrap this in parentheses and say I need 2 of them. And it's called, I hope I have room, ammonium carbonate. Alright, I think I'm getting better at writing, don't you think? Maybe not. Okay. Now, oops, what did I just do? Okay, now I have phosphate is -3. Tungsten can be a bunch of different things, but it's usually +6. So I'm going to put the tungsten first. I'll put the phosphate second. We're going to swap and simplify. I need 3 of these and 6 of these. So I say, well, 3 of these, 6 of those. But hey, wait, what's this? You can simplify that, can't you? So now I'm going to go ahead and say, yeah, you know what? Actually, that's the same thing as a 1-to-2 ratio. Whoops, what did I just do? So I'm going to erase that, and a 3-to-6 is the same thing as a 1-to-2 ratio. And I'm going to call that tungsten 6 phosphate. I don't think I have room to write phosphate, but pretend I did. Hey, is that the end of our homework? Let me look. Ooh, we're done. All right.